Hi guys, it's Sohim and Mahir here, and today we will be discussing Unit 13.1, that is Radiation and Radioactive Decay. So, radioactivity, as it was eventually named, appeared to be a fundamental property of an atom, and it was defined as the emission of radioactive particles from within a nucleus of an atom. Later research that was done by Rutherford and his colleagues revealed that these radioactive particles were of three basic types: alpha particles, beta particles, and gamma particles. So when an alpha particle is emitted by the nucleus of an atom, it is known as alpha decay. When a beta particle is emitted, it is known as beta decay. And when a gamma particle is emitted, it is known as gamma decay. Alpha particles have a positive charge, beta particles have a negative charge, and the gamma particles are neutral. To determine the charges on the alpha, beta, and gamma particles, Rutherford and his colleagues devised an experiment. What they did was that they put a sample of radioactive uranium inside a dense lead shield, and they allowed the emission of particles to pass through a magnetic field. So by using the right-hand rule for the charged particles in the magnetic field, we can see that the alpha particles will go towards the left because they have a positive charge on them. The beta particles would go to the due to their negative charge, and the neutral gamma rays would just pass straight to and would have no effect of the magnetic field. Now let's discuss the alpha particles in a little bit more detail. So the alpha particles detected by Rutherford were found to consist of 2 protons and 2 neutrons. Since a helium nucleus consists of the same number of particles, we can say that the alpha particle is equivalent to a helium nucleus. When a radioactive material emits an alpha particle, the nucleus of one of its atoms loses 2 protons and 2 neutrons. The loss of the 2 protons changes the atom from one type of element to another. This process is called transmutation. And the nucleus that is formed after the emission of an alpha particle is called the daughter nucleus. If an atom of an element, let's say X, transmutates into element Y by emitting an alpha particle, we say that a nuclear reaction has occurred, where the number of protons and the number of neutrons remains the same. A is the atomic mass and that is the atomic number. It is worth mentioning at this point that when an alpha particle is emitted by a nucleus of an atom, it can reach speeds of up to 1.6 times 10 to the 7 meters per second. Well, you might ask that where does the alpha particle get enough kinetic energy to reach this kind of a speed? Well, the theory of binding energy and strong nuclear force gives us a satisfactory answer. The strong nuclear force is a force that binds all of the neutrons and protons in an atom together. And the binding energy is required to overcome the strong nuclear force in order to break up the nucleus to emit an alpha particle. When we compare the mass of a parent nucleus with the sum of the masses of the daughter nucleus and an alpha particle, we find that the products of the nuclear decay are not quite equal to each other. The missing mass is converted into kinetic energy that is given by the Einstein's famous equation of E equals mc squared. Although the daughter nucleus and the alpha particle share the liberated energy, they do not share it equally. Recall that according to the law of conservation of momentum, if the mass of the daughter nucleus is significantly large than the mass of the alpha particle, then the speed of the alpha particle has to be way greater than the speed of the daughter nucleus. Now let's discuss the process of beta decay in further detail. Beta particles that are emitted in some of the radioactive decay may be negatively charged, that are the electrons, or they can be positively charged electrons, that are called positrons, or also known as anti-electron. So beta particles that are negatively charged are electrons, beta particles that are positively charged are positrons. Electrons are symbolized by 0, -1, and positrons are denoted by 0 and +1. It is important to note that the electron that is released in a negative beta decay is not one of the electrons in the orbital of an atom. The negative beta particle is produced in the nucleus of a radioactive atom. Although the mechanism of its production is a bit complex, it can be linked to the conversion of a neutron into a proton and an electron. So we can write that a neutron splits up into a proton plus an electron. Positive beta decay can also be considered equivalent to a proton changing into a neutron and a positron. We can write that in terms of the following equation. So one proton splits up into a neutron plus positron. So we can represent a beta negative decay by this equation. And a beta positive decay by this equation. Beta decay occurs in atoms that have too few neutrons in comparison with their number of protons. We know that the mass of an electron is approximately 2,000 times less than that of a proton. So according to the law of conservation of momentum, the recoil velocity of the daughter nucleus would practically be 0. And based on this, you would expect almost all of the energy released in the reaction to be found in the beta particle. As a reaction really produces just two particles, the daughter nucleus and the beta particle, the law of conservation of momentum requires the decay products to move off in opposite directions. But this did not occur. The two particles were found to be ejected at angles other than 180 degrees. Then in 1930, Wolfgang Pauli suggested an explanation. Perhaps there was another product in the reaction. The third particle would have zero charge and almost zero mass. Enrico Fermi named this particle a neutrino. Neutrinos are extremely difficult to detect since they have a very small probability of reacting with matter. Now let's move on to gamma decay and study that in a little bit of detail. Unlike alpha and beta decay, gamma decay results in production of photons that have zero mass and have no electric charge. This type of decay occurs when a highly excited nucleus, probably the product of another nuclear reaction, drops to a lower energy state while emitting out a photon of energy. If an atom of material Y emits a photon, that is the gamma particle, this is the symbolic equation for that. You can notice that no transmutation occurs. Gamma decay frequently occurs simultaneously with alpha and beta decays. And this is the end of the video. Hope you guys understood something despite my weird voice, and have a nice day.